as Dr. Andrew said, I will talk about the SSR origin in the galactic center. And first of all, let me just talk about the brief summary about the SSR. And as we all know, the SSR is this the young stars around the supermassive black hole in Sagittarius A in the Milky Way. And what we know is they are massive stars and young, and they have a short period, it's a short orbit period, And in my presentation, I will talk about the two papers I've read, and I will just say a brief summary of the introduction and what they found of the three massive clusters in the galactic center. And after that, I will shift gear to the stellar orbit model from the other paper I've read. And before that, I will just talk what they actually did before and go to the method they used for. And finally, I will just give a summary of what I presented. So, as I've said before, this star it's the stars around the supermassive black hole, and what they studied is the stars around Sagittarius A are the closest stars around the Sagittarius A in 0.2 parsecs, and has an age of 10 million years, which they are still young now. As we know that the age of the sun is approximately 4 billion years, and as I have said, the orbit of the S star are really short. Some of these stars are the orbit are in 15 years or more or less. And the discovery of the three massive cluster, which is as I wrote it here, the central cluster and the Arches cluster and quintuple cluster. So the central cluster, they contain really massive stars. They contain 80 massive stars, and most of this, the majority of stars have the age of 10 million years, and most of them are OB type stars, OB supergiant type stars, and the mass of the cluster is 10,000 solar masses, and the picture on the right, it shows it takes in K band, and it shows that the all brightest stars are around this in the picture. It's the O-type stars, and the square in the middle is the S stars around the supermassive black hole. And these stars are really not that massive. It's just 20 solar masses, but the all central cluster is 10,000, as I've said before. And the second cluster is the Arches cluster, which which they are really really massive, and the ages are really like younger than the central. And the central cluster, as I've said before, they have a period of 10 million years, but for the Arches cluster, they have just a age of 2 million years, which they are young. And the most the most like the stars in the Arches cluster contain extremely high masses stars with relatively young stars, and they mostly contain the O type stars and WNR, which is the Wolf-Rayet mixing with the nitrogen. And the picture on the right also shows the Arches cluster obtained from Dr. Feiger by HST, Hubble Space Telescope, and it shows that the brightest stars in the picture has a mass of 100 solar masses with in O type stars. Next is the quintuplet cluster. As I said, for the Arches and the central cluster, the quintuplet cluster are still young, with 4 million years old, with 10,000 solar mass, and they're known for its the 5 very brightest stars. Like, they contain really bright stars compared to the other cluster I've shown before. And what they found in the quintuplet cluster, they have the dusty Wolf-Rayet mixing with the carbons, the Wolf-Rayet stars, dusty Wolf-Rayet star. And in the paper, this shows that what they found, that they have this, like, these stars is the dusty Wolf-Rayet star, and they have two explanations of why they are dusty. And the two explanations, one of them is the binary fraction of the massive stars are really high, and the second explanation is that the binary massive stars evolve through the WC, the late Wolf-Rayet stars phase, Wolf-Rayet phase. So I made this table to show you, like, as I've said before, the Arches are really massive and young compared to other clusters around in the galactic center. And as you see now, it's the mass the log mass. As you can see here, is the Arches cluster has the log mass of 4.1 solar mass, and the ages of between 2 to 3. But compared to the central and the quintuplet, the Arches are really massive and really young. And like most of them are the O-type stars. So this table, I show you all the information of, like some information of the clusters and the stars in the cluster. But in this table, I've shown that is the cluster, what type of stars inside these clusters. And as I said before, the O-type stars, just like the majority of O-type stars, it's just in Archie's cluster, and there is no luminous blue variables or WC or red supergiant in Archie's. So switching from the clusters, the stellar cluster in the Milky Way, to the stellar orbit models, what I've said before, it's from the other paper. So a brief introduction about the other paper. They measure the three stars, the closest three stars to the Sagittarius A. And all these stars have the age of 10 million years, with really close orbit near the supermassive black hole, which is 0.01 parsec. So they use for this star, they use the model called Kozai mechanism, and for binary stars. And when they use the Kozai mechanism for the binary stars and the eccentric orbit, they found out that the S stars get distributed, and the stars get distributed and leave behind the S stars and the hypervelocity stars. And the image on the right, it shows the two stars orbiting if the first stars, the M1 stars, orbiting the black hole, and the M2 stars orbiting farther out, so the M1 gonna affect the gravity of the other stars, which they call it is the Kozai mechanism, which is if the first star orbiting the black hole and the other star is orbiting farther out of the first star, the gravity affect the first stars more, affect more the first stars than the second one. So here's the graph that shows the eccentricity evolution of stellar orbit in given time. And what they did, they took the three stars I said, it's the closest three stars to the black hole, and what they found that one of this, when they test the Kozai mechanism, it's impact one of the stars, three stars, and give the that stars the high eccentricity. So the okay, this is the first stars, and the solid line is the second stars, and the dot line is the third star. So the first star has the the closest star is the one which shows in long dash, and has the highest eccentricity, which goes to like almost 1, like close to 1. But the other two stars, it goes to close to 0.9 and 0.99. And here, what they did, they calculate the intermediate mass black hole of the stellar binaries to test the impact of Kozai model. So what they did is they showed the ages, the time. They show the 3 stars in given time, in the ages, with the semi-axis for binaries, for the semi-axis, semi-major axis, and the eccentricity. And what they show, the outer and the inner eccentricity shows that the outer eccentricity grows due to the Kozai mechanism, which they show here for the long dash, and shows that from the Kozai mechanism as affect the growth of the outer eccentricity, but the inner eccentricity stayed the same with semi-axis. The semi-major axis, and for the semi-major axis, the outer and the inner are still the same, but for the inner eccentricity, it goes constant and until the age of 5, almost 5, and drop in here. For the outer eccentricity, grows so fast after the age of 3, grows so fast, and due to the Kozai mechanism. Okay, in summary, for what I've said, the S star, the majority of S star, they show that has the O and B giant and the Wolf Rayet star, and the majority of S star are B type than the O type star, and of a factor of 5. The equal mass binaries has the mass of 20 solar mass, which they believe that the S star and the disk star formed in the same environment. So so the S star and the disk form in the same environment. So the O type star has the B type star has the majority than the O type star, and the O type star didn't form in a tight binary as they're required to produce the S star. Okay, thank you.
Thank you, Abdul.
Is there any questions?
Questions?
What is your science questions for this project?
What's the S star origin in the galactic center? So I didn't actually solve the question. I didn't actually answer the question, but I hope like in the future I can like observe the stars around the supermassive in outer region, not the region they use, like less than 0.5 parsec. If I can go like to 1 parsec or 2 parsec and see the stars around.
What do you think that will tell you?
If I see because what they said is the stars around the supermassive black hole in the region that they used, they say that they are really young, but they are really young in the formation of the star, but they are actually not young. They are actually merging with, like they are actually old star merging with young star, which like make them as what we see now as young.
Okay.
So
you're talking about the S stars here, right?
Yeah.
Okay. So they appear young because they
merge. They're actually old, but when they merge with the young star, they say that the theory behind is that they are actually old star, but when they merge with the young star, they become young.
Maybe their metallicity change or something. Yes.
Other questions? Right. So you told us about S stars, and you told us about the massive clusters. What's the? Maybe you said this, but I missed it. What's the connection between the two?
All the cluster I've shown is all massive S star cluster.
I see.
Like all the stars is S star. So what they said is the S star is actually the OP type stars in the cluster. So
are you saying that the S stars originate in the clusters, or are they still gravitationally bound members of the clusters?
the members of a cluster.
Even though they're orbiting the black hole?
What? Sorry?
They're orbiting the black hole.
Yeah.
Essentially. So they're still considered members of the cluster.
Mm-hmm.
Oh, there were 3 clusters you talked about.
Yeah.
Are there stars in each of those?
There are many stars in each, as I shown here in the.
So are these the same S star that we use to identify the location in the mass of Saturday star? Or are they just like different group of S stars?
Yes, when I think of S stars, I think of the stars that have been tracked orbiting the central black hole.
Is that the same?
Are we talking about the same stars?
Yeah.
Okay. Questions? So you say that we know the age, 10
Mhm.
megayears or so. How do we know this? What's the evidence of that? And the mass for that. How do we know that masses of these things?
Not sure.
Whereas you said they're not in binary systems, right?
Yeah.
So that would be the way that you would measure the mass of a star by its orbital parameters in a binary. But if they're not in binaries, how do you know the mass? things you would measure if it was a binary system. Sure. Okay, all right. Do you know how the age has been established, please?
They say that for the edges of each cluster, they said the majority of the stars around it, the edge established for the cluster is the majority of the stars inside that cluster. So each star has like different age, but all like between 2 to 3, like in each cluster. Like for the edges, as I said, it's from 2 to 3, and for the central, it's less than.
So the S stars are assumed to have the age of the cluster that they are associated with, right? So how is the cluster age found? Do you know? I guess by looking at the main sequence turnoff.
Mm-hmm.
I don't know how it's done in this particular case, but that would be one way. Anybody know?
I would say, well,
What would make it exactly?
yeah, I would say main sequence turnoff is probably one.
So if you construct an HR diagram for the cluster,
Mm-hmm.
and you can put the main sequence stars, see where the main sequence is, and in general there will be a turn-off point as stars, but the more massive stars are more quickly.
Yeah.
Right, so they turn off the main sequence. And that point tells you the age of the cluster.
So you do for like for the stars as the edge, like if the cluster has 100 stars, so each of the one has like the age of.
Well, it rests on the assumption that all of the stars in the cluster were born at the same time.
Mm-hmm.
That's the assumption. Right, so more massive ones evolve more quickly.
Yeah.
And leave the main sequence. That turn-off point will move down the main sequence as the cluster ages. So its position on the main sequence tells you how old the cluster is, and therefore how old the member stars are. Just one last thing then. So you talked about the Kazai mechanism.
Mm-hmm.
Can you go back to the diagram? That one. Can you explain what that diagram is again, please?
This one?
Yeah. So.
Yeah, this is like as I've said before, is the Kazai mechanism is if the star orbit the supermassive black hole, so the effect of the gravity of the first one is by the second star orbiting outside.
Okay, can you actually point out where the black hole is on that diagram?
So, like, it's not the black hole in here, but what I'm saying is like if it's here, like in the middle, in the X, that X. So for binary star on eccentric orbit around the supermassive black hole, they
So what is that
Yeah.
X? Is that the center of mass?
Mm-hmm.
Okay. Further binary?
For this orbiting, like the star orbit, this one, so the gravity effect of the inclination of the other star orbiting out.
So it's a 3-body interaction.
Yeah.
Any other questions?
Would M0 be the supermassive black hole?
The M0, the mass of the the black hole.
Sorry, is M0 the black hole? Is that what you're saying? I
No.
thought you said that was the other member of the binary.
No, this is like the two binary stars, the M1 and the M2.
Okay. Wow.
But this one is like the center is the mass of the black hole. Like if we just assume that.
So
the black
M0
hole
is the black hole.
Mhm.
Okay, that's what I was trying to establish.
Mhm.
Right.